It's the observation that when you take skin cells from a frog embryo and you liberate them from the instructions that normally say you're going to have a very boring life. You're going to sit there quietly as a two-dimensional layer on the outside of um, the embryo, and you're going to keep out the pathogens. That's what you're going to do. And so when you liberate cells from that condition, you take these skin cells, you put them in a different environment, and you basically say, well, now you don't have those instructive cues. You can reimagine your multicellularity. What are you going to be? Right? What are you going to do? And they could have done all kinds of things. They could have crawled off. They could have made a monolayer like a cell culture. They could have died. They could have done all sorts of things. Instead, what they do is they come together in about 48 hours. They come together and they form this new creature that we call a xenobot. For Xenopus laevis is the name of the frog, and it's a biobot. And it makes this little proto-organism that does all kinds of amazing things. It swims around on its own. It has all kinds of behaviors. It has group behaviors. It has individual behaviors. It can regenerate if you damage it. It does all these interesting things. So one of the most amazing things that it does is that because it can't reproduce the normal way, because it doesn't have the normal frog reproductive organs, it figured out a completely new way to replicate itself. So what it can do is if you give it a bunch of loose cells, it basically does a version of what von Neumann was toying with, this idea of a replicator that goes around and collects parts and then builds a copy of itself. They basically run around and they herd like sheepdogs. They herd a bunch of loose cells into little piles and sculpt them into other xenobots. And then guess what they do? They will run around and do the same thing. And there's 3 or 4 generations down. So. And there's no genomic editing anywhere here. If you sequence these things, all you're going to ever see is Xenopus laevis, and you have no idea. You would have zero. This is going back to that idea of how much do we really know about the genome and the anatomy if you can have something that acts and looks in a completely different way and has the same wild type anatomy with the same wild type genome, right?
And do you think that this is possible with cells from other organisms, or is there something special about?
There's nothing froggy about this. I can't go into details now because I don't talk about unpublished work, but
Sure.
in these contexts. But I can just tell you this has nothing to do with frogs. It's a much more nor embryos. It's a much more general phenomenon.
So you think that you could make something like this from human cells?
Yeah, we will see. Stay tuned. We will.
Whoa!
Need some permission for that, probably. But,
we'll see.
yeah, I want to
put that on your calendars.
So let me just finish that
Sure.
point. So this is what they're doing with their standard genomes, right? And what I think is really significant here is that for every other creature on Earth, if you ask the question, why does it look the way it looks? Why does it have the behavior it has? Why is it this color? Why does it have this many eyes? The answer is always the same, because for millions of years, the ancestors were selected for this and that. That doesn't exist here. These things never existed before. All of these cells were selected to be a nice, quiet skin layer, right? Instead, on their own, they have a much more exciting life. They're autonomous. They run around. They do all kinds of stuff. So the question of where do these things come from? Where does its body plan come from, right? If you ask where does a frog body plan come from, well, people will say, well, selection, millions of years of selection for being a nice frog. Well, where does xenobot bodies come from? There's never been selection.
It's artificial selection, is it not? I mean, if you're scraping off this skin cell versus that,
but we're not selecting them. But we're not selecting them. I mean, we do not know anything that it takes to build a robot that does this kind of stuff, right? The answer to how does it know to do all these things is not because Mike and Josh made them do it. I mean, there's a component of the project where we use machine learning to kind of nudge them towards specific outcomes, right? And that's very important to learn to do this.
Is that AI by tuning the soup or something, or?
Not yet, although that's where it's going. Up until now, we've just been sculpting. The AI says, if you just cut away of some cells from here to there, they'll move better or they'll do certain things. So look, there's 3 really important things about all this. One is that it's at some point we'll have useful synthetic living machines. So they'll be scraping the plaque off your artery walls or chasing down tumor cells in your gut or something. There's all kinds of useful applications. The second thing is that they're teaching us about how do collectives of cells make decisions about what to be. That's the answer to regenerative medicine. The whole field of regenerative medicine is basically stuck because we don't know the answer to that question. how do collections of cells make decisions about what they're going to do? The genome is not the answer. Stem cell biology is not the answer. We do not understand how collectives of cells make decisions, large-scale decisions. This is a sandbox, a platform. It's a very simple system. It's one type of tissue, just skin. Okay, so ultimately, what this is for, way beyond useful machines, is we are going to try to understand how do cells get their goals? Collectives of cells get their goals. Where did the goal of being a Xenobot come from? Because it showed up in 48 hours, did not require millions of years of evolution. So the question is, where did that goal come from? And more importantly, how do we re-specify it? So if I said, that's great and all, but I don't want a round Xenobot, I want a long flat one, and I want it to do this and that. Like what are the signals that I need to give you? Because once we crack that, that's the key to proper regenerative medicine, where we can make new organs, we can fix birth defects, we can reprogram tumors. So all
is
of
that because
right?
you'd understand the goals of the organ cells, and you could kind of give them what they want, and they'll just execute their actions?
It'll be a combination of giving them what they want, meaning incentivizing them with rewards and punishments, and a combination of re-specifying the goal states. Just like in the planaria, if your goal state for whatever reason is screwed up and you think you're going to be a tumor, I got a better goal state for you. Here's a new pattern memory that you're going to follow, and I'm going to incentivize that with a little bit of whatever reward or punishment or whatever you're going to do. And then the bigger picture, and this sort of takes us back to this conversation about like society and everything that we were talking about. The bigger picture, I see this as an existential, as mitigation of existential risk for humanity. I mean, look at this. We are surrounded by systems, large-scale systems like Internet of Things, computer networks, swarm robotics, social structures, financial structures. We have only the barest beginnings of a science of knowing what do these collectives want as goals. We have absolutely no idea.
In some way, we've turned ourselves into cells that are part of a larger organ.
That's correct. And the cells have no clue what the organism is going to want to do. What are the goals of the larger scale system? In fact, if you think of shrinking yourself down to the level of a single cell inside of an early embryo, and you're looking around and you're seeing all the stuff that's happening and all the noise and chaos, and cells are dying off and moving from it, falling off and all this stuff. Would you ever in a million years know that this is going to make a 100% reliable fish or frog or human? You would never know that. If you didn't already know about embryonic development and the fact that it was reliable, you would never know that that's what was going to happen.
No, go ahead, sorry.
Well, just to finish up. So we are surrounding ourselves with complex systems that are going to have goals. Those goals are going to be different from ours. They're going to be as inscrutable to us as the goals of the organism are to the cells. When you think about your goals in the morning or your life plan for the next 3 years, the cells in your body and the organs and the tissues don't even have the beginnings of a cognitive system to appreciate what's going to go on here. Right? We're surrounding ourselves with this, and we do not have a good science of anticipating and managing collective goals. So my point is, if we can learn from some frog skin, which, by the way, frogs are shedding into rivers all the time. So, people get all crazy about this, but that's another thing. People say, oh my God, these Xenobots, this is frog skin for God's sake. You understand that we've had synthetic bacteria, viruses, both natural and synthetic. We've had germ warfare. We've had genetically modified, organisms being released. Like, compared to all of that, this should be so far down on your list of things to worry about. It's ridiculous.